This video is going to define the definite integral and connect that definite integral to the Riemann sums that we discussed in the previous section. So we're going to start by just solving an area problem. Find the area between the x-axis and the function f of x equals x plus 2 from x equals 0 to x equals 3. And we're going to start by finding this area using geometry. So I'm going to draw a picture. Our function is a line. We have the line y equals x plus 2, so that has a y-intercept of 2 and a slope of 1, so up 1 over 1. So that's my function. I want to find the area under this curve, between this curve and the x-axis, from x equals 0 to x equals 3. The shape I have is a trapezoid, so I can actually use geometry to find this area. Rather than looking up the formula for area of a trapezoid, though, I'm just going to divide this region into a triangle and a rectangle, since I know those formulas. The area of a triangle is 1/2 base times height. So I have this little triangle on the top of my image. This triangle has a base that is 3 units. And its height, it starts at y equals 2. And when x is 3, if I plug that in here, 3 plus 2 is 5. So this would be the point 3, 5. So from y equals 2 to y equals 5, we've gone up 3 units. So base is 3, height is 3, 1/2 times 3 is 9/2, or 4.5. And then the bottom part of this object is a rectangle. Area of a rectangle is just length times width. Length is 3 units. The width would be 2 units. 3 times 2 is 6. And so my total area would be the sum of those two quantities, or 10.5. So that's the area under this curve. Now let's see if we can get this same answer using our Riemann sum limit process. So this is exactly what we did in the previous video. We're just repeating the process as a really nice review. So let's see if we can find the area using n rectangles with right endpoints and letting n go to infinity. So if we have an infinite number of rectangles, what is that area? So to start, if I'm dividing this region up into rectangles, the width of each rectangle, the delta x, is the length of my interval divided by my number of rectangles. The length of the interval, stopping at 3, starting at 0. So 3 minus 0 is 3. So the width of each rectangle is 3 divided by n. If there's n rectangles, width would be 3 divided by n. All right, height of my rectangles with right endpoints is going to be f of a, my starting point, which was x equals 0, plus my width times I, where I is an integer starting at 1, going up to our number of rectangles. So f of 0 plus 3 over ni, or f of 3 over ni. Plugging that into my function, so f of 3 over ni, I plug that in for x, I get a height of 3 over ni plus 2. So my rectangles have a width of 3 over n and a height of 3 over ni plus 2. So that means the area is going to be the width times the height. So that would be the area of each rectangle. And if we have n rectangles, we're going to add up, using this sigma notation, the area of each rectangle. So when we have n rectangles, we're going to create a sum from I equal 1 to n. So first rectangle up to the nth rectangle of our width times our height. I'm going to go ahead and distribute that 3 over n. That gives me 3 over n squared I plus 6 over n. And then I can simplify this sum using those formulas we learned in the previous video. So when you have the sum of a constant from I equal 1 to n, you're going to get that constant times n. And when you have the sum of I from I equal 1 to n, you'll always get n plus 1 over 2. So the 9 over n squared is a constant, and the 6 over n is a constant. So adding up this I times my constant, 9 over n squared, I should get 9 over n squared, my constant, and then I used my sigma formula for adding up the I. So adding up that I, it becomes n plus 1 over 2. 6 over n is just a constant. There's no i's in that term. So adding up a constant, we get the constant times n. So 6 over n times n. All right, I'm going to do some algebra with this. So here's the expression I have for area when we have n rectangles. We can simplify. We've got a common factor of n in the first term. So that leaves me with 9 times n plus 1 over 2 times n, or 9n plus 9 over 2n. And then the second term also has a common factor of n, so it simplifies all the way down to 6. Finally, we're going to see what happens if we let n go to infinity. So what if we have an infinite number of rectangles? That should give us the exact area. When we have a finite number of rectangles, we're just getting an approximation. But if I let n go to infinity, so I'm going to take the limit as n goes to infinity, and that should tell me what the exact area under the curve is. So if I take my infinity and I plug it into that first term, I get infinity over infinity. So I decided to divide everything by the largest power of n, which is just n to the 1. I got 9n over n plus 9 over n over 2n over n. That simplifies to 9 plus 9 over n all over 2, and then plus 6. You could also use L'Hopital's rule to find the limit of that first term. Because you're getting infinity over infinity, that indeterminate form, you could take the derivative of the top and the bottom as well. Okay, but continuing with the method that I'm using, I'm going to plug in infinity for n. So 9 divided by infinity, finite number divided by infinity is going to go to 0. So this limit is going to become 9 over 2 plus 6, which is 10.5. And that is the exact same answer I got when I'm using geometry. This is the area under that function. Now, I want to introduce the definite integral. So earlier, when we talked about antiderivatives, we were computing indefinite integrals. We used this integral symbol, but we didn't have little numbers on it. And that notation, the integral symbol f of x dx, represented the antiderivative of a function. The definite integral has little numbers with the integral symbol. Those are referred to as the bounds of integration. And I have written on the screen the limit definition of our definite integral. Our definite integral of a function is actually defined by a Riemann sum with that limit process. So our definite integral is actually going to give us the area between the function y equals f of x, the function you're integrating, and the x-axis. So it's going to give you the area under the curve from x equal a to x equal b. Those little bounds of integration, those numbers, tell you the x value you're starting at and the x value you're stopping at. It's going to give you the area under the curve if that function is bigger than or equal to 0. If that function is less than or equal to 0, it'll actually give you the negative area. And we'll say a little bit more about that later. But our definite integral is actually defined by our Riemann sum. So let's see how this works by doing an example. Let's use a Riemann sum to find the following definite integral. Negative 1 to 3, 9 minus x squared dx. So in this problem, the function we're working with is 9 minus x squared. So we're working with the function 9 minus x squared from x equal negative 1 to x equal 3. This integral is actually asking us what is the area under that curve from x equal negative 1 to x equal 3. So we're going to set this up using our Riemann sum process. My delta x, the width of the rectangles, is the length of the interval divided by n. So I did 3 minus negative 1, that's 4, divided by n. So if I have n rectangles, width is 4 divided by n. I'm going to use right endpoints. You can use right or left endpoints because we are taking a limit as n goes to infinity, so it actually doesn't matter, but it's easiest to set these up with right endpoints, so that's what I'll do. So my height is going to be f of a, the starting point, so negative 1, plus my width, 4 over n times I, where I is an integer from 1 to n. Plugging that into my function, so the function is 9 minus x squared, so the height would be 9 minus negative 1 plus 4 over ni squared. I'm going to go ahead and simplify that expression. I will FOIL out the minus 1 plus 4 over ni squared. I get 1 minus 8 over ni plus 16 over n squared I squared. So I got that using FOIL. And then we're going to take 9 minus that quantity. So I have to distribute the negative 1 to everything inside the parentheses, and then I can combine like terms to give me 8 plus 8 over ni minus 16 over n squared I squared. All right, so that means the area of n rectangles is going to be the sum from I equal 1 to n. So first rectangle to the nth rectangle of the width of my rectangles times the height of my rectangles. So 4 over n times 8 plus 8 over ni minus 16 over n squared I squared. And just as a side note, notice that when you set up your Riemann sum, the 4 over n is your delta x, and if we make that infinitely small, that becomes a dx. The height of your rectangle comes from your function, your f of x, and then we have a sum, and when we apply the limit process, that sum we actually rewrite as that integral symbol. So we're taking the integral of f of x dx. So just a little side note, that's where that notation comes from, because the integral symbol tells you you're adding up your function times dx, basically. All right, so what are we doing though? Back to what we're doing. We need to compute this Riemann sum. So I'm going to distribute the 4 over n. That gives me 32 over n plus 32 over n squared I minus 64 over n to the third I squared. Now I'm ready to apply my summation formulas. The 32 over n is a constant, so that's going to give me 32 over n times n when I do that sum. Then I have 32 over n squared, which is a constant, times I. When I do that sum, I'll get my constant, 32 over n squared, times my summation formula for I would be n plus 1 over 2. And then the last term, this minus 64 over n to the third, that is a constant. When I add up those terms, I will get that constant times my summation formula for I squared, which is n to n plus 1 over 6. All right, so I have a complicated expression now that gives me the area when I have n rectangles. I'm going to simplify. I have some common factors of n. Actually, in all 3 of the terms, I have a common factor of n. So I'm going to go ahead and cancel those out. First term, I end up with just 32. Second term, I canceled out an n. I also have a common factor of 2. So that's going to become 16 n plus 1 over n. And then my last term, I did have a common factor of n. And I have another common factor of 2. So canceling that out, I get 32 times 2n squared plus 3n plus 1 over 3n squared. Then I distributed, so I got rid of parentheses. So 32 plus 16n plus 16 over n minus 64n squared plus 96n plus 32 over 3n squared. Finally, we want to see what happens when we take the limit as n goes to infinity. What happens when we have an infinite number of rectangles? So I'm going to take the limit as n goes to infinity. And this time to find my limit, I decided to just do a little bit more algebra. Because these fractions have only one term on the bottom, I can actually break up the numerators. What I mean by that is this 16n plus 16 all over n. We can write that as 16n over n plus 16 over n. And I can do the same thing with the last term as well. I can rewrite each term on the numerator as something over 3n squared. And then I can do a little bit more algebra because I can simplify. I've got some common factors. So 16n over n is just 16. So now we've got 32 plus 16 over n minus, next term the n squareds cancel out, so that becomes 64 over 3. Next term, common factor of n. Common factor of 3 as well, so that becomes 32 over n. And then the last term can't be simplified. That one is just 32 over 3n squared. Finally, I'm going to take the limit as n goes to infinity. Anytime we have that finite number over infinity, that's going to go to 0. So we are just left with 32 plus 16 minus 64 thirds. That simplifies all the way down to 80 thirds, or 26 and 2/3. And that is the value of this definite integral. Now, because definite integrals represent area under the curve, as long as the function values are greater than or equal to 0, if we have simple shapes, we can actually use geometry to compute definite integrals. And I want to show you a couple examples of that. Let's find the integral from 1 to 4 of 5. So I'm going to start by drawing a picture. The function that we're dealing with is f of x equal 5, or the line y equals 5. That's a horizontal line. My bounds of integration are 1 and 4. So we are trying to find the area under that horizontal line, y equal 5, from x equal 1 to x equal 4. I have a picture drawn of exactly what we're trying to compute, and I can see that the area that we're trying to find is actually a rectangle, area of a rectangle. The width of this rectangle, going from 1 to 4, is 3, and the height of my rectangle is 5. So area would be 3 times 5, or 15. And that is the value of this definite integral. I was able to use geometry instead of a Riemann sum here because I had a simple shape. Here's another one. We have the integral from 0 to 3 of 2x plus 1. So my function is f of x equal 2x plus 1. That would be a line with a y-intercept of 1 and a slope of 2. So up 2 over 1, up 2 over 1. I want to find the area under this curve from x equals 0 to x equal 3. This reminds me of the problem we started with. This region is technically a trapezoid, but I can divide it up into a triangle and a rectangle. To help me find my area, I might label some points. So I do know that my y-intercept is at y equal 1. And then the right side of this object, when x equal 3, if I plug 3 into this function, 2 times 3 plus 1 is 7. So that should be the point 3, 7. And so looking at my picture, I have a triangle. My triangle has a base of 3 and a height starting at y equal 1, going up to y equals 7, so the height would be 6. So 1/2 base times height would be 1/2 times 3 times 6, that's 9. And then I have this little rectangle here that has a base of 3 and a height of 1. So 3 times 1 is 3. So total area would be 9 plus 3, or 12. And again, that is the value of my definite integral. Had I used the Riemann sum and a limit process, I would have gotten the exact same answer. All right, here's one more. Now we've got the integral from -3 to 3 of the square root of 9 minus x squared. So the function we're dealing with is y equals the square root of 9 minus x squared. We want to find the area under that curve from x equal -3 to 3. So I'm going to draw a picture first. And so to help me visualize this function, we could square both sides. Let's get rid of the square root. So if I square both sides, I get y squared equals 9 minus x squared. And then I can add x squared to both sides. I can move the x squared over to the left, and this becomes x squared plus y squared equals 9. X squared plus y squared equals 9 is a circle that has a radius of 3. This is the equation of a circle centered at the origin with a radius of 3. The standard equation of a circle centered at the origin would be x squared plus y squared equals r squared. Now, because our function is a positive square root, y equals the positive square root of 9 minus x squared, that is actually just the top half of this circle. The y values are positive on the top half of the circle. The bottom half of the circle would actually be the equation y equals negative square root of 9 minus x squared. But we're just dealing with the top half of the circle, and we want to find the area under that curve from negative 3 to positive 3. So technically what we're doing here is we're trying to find the area of half of a circle. And once again, this is something that I can do using geometry. I know that the area of a circle is pi r squared. I want to do half of that area. So the area of a semicircle would be 1/2 pi r squared. My circle has a radius of 3. So 1/2 pi 3 squared becomes 9 pi over 2. And again, there's the value of my definite integral. That was something I could do with geometry because I had a circle. All right, I want to give you a couple properties of definite integrals. So first property says if you're integrating a function and your lower bound and upper bound are the same, you're going to get 0. So thinking about this using geometry, this is just telling us if the left side of our object and the right side of our object are the same, the region we're trying to find the area of has a width of 0, so our answer is going to be 0. Second property says if you change the order of those bounds of integration, so normally our lower bound is going to be our smaller number, and our upper bound is going to be our bigger number, and that's going to give us area under the curve. But if we switch the order of those bounds of integration, it's just going to change the sign of the answer. We'll get our negative area. The third property says if you want to integrate from a to b, you can actually break this up into two separate integrals and integrate from a to c, and then integrate from c to b and add those two things together. I can understand that using area. If I want to find the area under this curve, I could divide it up into two regions, find those areas separately, and add them together. It turns out, though, this actually works where c can be any number. C doesn't have to be between a and b, but it's easiest for me to explain it with a picture if I put c in between a and b. But a, b, c could be any numbers, and this property would work. Next property says if you want to integrate a constant times a function, you can pull that constant out front and just integrate the function. And then multiply it by the constant. And this property comes from the fact that these are Riemann sums. And when you have a constant, you can use that distributive property and just pull that constant out front. And then finally, last property says if you want to integrate a sum or a difference of functions, you can add or subtract those two integrals. You can integrate each function separately, add or subtract them. And again, that comes from our Riemann sum idea. When we have sums and differences, we can find the Riemann sum of each part separately and then add them together. All right, so let's use these properties to actually solve some problems. We are told that the integral of x squared from 1 to 3 is 8 1/3. The integral of x from 1 to 3 is 4. The integral of x squared from 3 to 4 is 12 1/3. And if we integrate from 1 to 3, just 1 dx, we get 2. Let's use these facts to solve some other problems. I want to integrate x squared from 1 to 4. And so in this problem, I notice that I'm told what the integral of x squared is from 1 to 3, and then I'm told what the integral is from 3 to 4. So if I add these two values together, that will give me the integral from 1 to 4. I'm essentially finding the area from x equal 1 to 3, and then the area from 3 to 4, and adding those two things together. So 8 1/3 plus 12 1/3 would be 20 2/3. The second property, we're integrating 8x plus 2 from 1 to 3. We have a property that says if we have a sum of functions, we can split it up and do each part separately. So I can rewrite this as the integral of 8x from 1 to 3 plus the integral of 2 from 1 to 3. And then I have another property that says if there's a constant times a function, we can pull that constant out front. So this is going to become 8 times the integral of x dx plus 2 times the integral of 1 dx. And finally, at the top of my screen, they told me what the integral from 1 to 3 of x is. It's 4. And the integral from 1 to 3 of 1 dx is 2. So just plugging those values in, I'm going to get 8 times 4 plus 2 times 2. And that simplifies all the way down to 36. All right, one more. My last one's really similar to the one I just did. Now I have integral of 6 minus 2x dx, a difference of functions, so I can split this up into integral of 6 minus integral of 2x, and then I can take those constants and pull them out front. So I get 6 times the integral of 1 dx minus 2 times integral of x dx. And once again, at the top of the screen, I know that the integral of x dx is 4, and integral of 1 dx is 2. So plugging those values in, 6 times 2 minus 2 times 4 simplifies down to 4. Finally, in my last example, I want to come back to this idea of area and show you what happens if our function is actually below the x-axis. What happens if our y values are actually negative? And so I'm going to illustrate this by just doing an example. We are given a picture of a function, and we're told what the area of certain regions are on this graph. And we're going to use the graph to find several integrals. If I want to find the integral from 0 to 2 of this function of f of x dx, that integral is going to represent the area under the curve from 0 to 2. And I can visually see on the picture that area has been labeled as having a value of 2. So part A, this integral represents the area under the curve. I can see that my function has positive y values. It's above the x-axis, and that area is 2, so answer is 2. What if I want to integrate from 2 to 4? So if I'm integrating from 2 to 4, now in that region, the function is entirely below the x-axis. I know that the area of that region is 5, but anytime your function has negative y values, the integral is actually going to give you the negative area. Those y values that you're adding up in your Riemann sum are actually negative. And so if the area of this region is 5, but because it lies below the x-axis, that answer is going to be negative 5. Finally, integral from 4 to 5, that's referring to this last region here. The area is 2, so that area would be 2. We can put these ideas together and find other integrals using the same image. So for example, if I want to find the integral from 0 to 4, part of the function lies above the x-axis, and part of the function lies below the x-axis. So what I can do is I can take my answers from part A and B and actually just add them together. So I know if I integrate from 0 to 2, I'm going to get 2. I already did that. I'm going to get 2. And if I integrate from 2 to 4, I'm going to get negative 5. So my final answer should be 2 plus negative 5 or negative 3. So what's happening here is if your function has parts of the graph that are above the x-axis and parts of the graph that are below the x-axis, this integral is no longer giving you an area. It's giving you something related to area, but some of those positive and negative areas are actually canceling each other out. My answer of negative 3 tells me that more of the function is below the x-axis than above. but that's all it tells me. It doesn't actually tell me the area. And then finally, if I want to integrate from 0 to 5 all the way across this picture, I can just add up each component or each integral separately. So what I mean by that is from 1 to 2, we have an area of 2. From 2 to 4, my integral is going to be negative 5 because our function is below the x-axis. And then from 4 to 5, our area is 2. So 2 plus negative 5 plus 2 gives me negative 1. All right, that was my last example in this video, so please reach out if anything is unclear.